This will lead to a variation of the total entropy of the ball, one term coming from the area change with some universal coefficient. I'm just going to assume that there's some area law here for entropy. And then the IR piece is just, the interior entropy caused by changing the quantum state, like putting that particle inside. And because I'm considering first order variations, when I consider this variation, I can hold the geometry fixed. When I consider this variation, I can hold the state fixed. And so it's easy to calculate the two terms separately. This term, if we wrote the density matrix inside the ball as e to the minus some operator, then it's just an algebraic fact that the variation of the von Neumann entropy of this density matrix when I change the state is the variation of the expectation value of this operator. This is like the Clausius relation that d entropy is d energy expectation value over temperature. So that's, well, in order to calculate this term, we're going to have to calculate the variation of this exponent's expectation value. This term we've already computed geometrically. So how do we calculate this K variation? Well, there's a technology that goes back to some sort of parallel work by Lashkari, McDermott, and Van Ramsdonk a couple of years ago in a holographic derivation of a linearized Einstein equation off of anti-de Sitter space. And it's using something called the Ryutakinagi formula for entanglement entropy. I don't have time to go into that, but I just want to mention that I'm just borrowing the same technology. They were using it in the context of a conformal field theory. That's the CFT side of ADS CFT. Whereas I want to use it in space-time itself, which presumably is not described, where the quantum fields are not described by a conformal field theory. But I'm going to nonetheless start out by assuming it is a conformal field theory so I can see what I get using this, and then I'll try to generalize it to a non-conformal field theory. Okay, so I'm going to skip most of these details. The key thing is that in Minkowski space, if you take a ball and you look at the causal diamond, that's its domain of dependence, that has a conformal killing vector, which I've written out here in some coordinates. And the whole region in that conformal killing vector is conformally related to the wedge of Minkowski space with its boost killing vector. Therefore, if you have a conformal field theory, you can conformally map the problem of the entanglement of the state inside this diamond to the problem of the state inside the Rindler wedge. And there we know the answer. Going back to Unruh and Bisignano-Mickman, we know that the state, as I mentioned earlier, is thermal in the wedge. So we can just use that mapping to tell us that the state in here is the exponential of the generator of this conformal boost, which I can write in terms of the stress energy tensor as an integral over the ball of the stress tensor contracted with the conformal boost killing vector integrated over the ball. Then I take the expectation value and I vary it, and here's that Unruh temperature again appearing. So I would have this formula. Now I want to take the ball small enough that I can take the expectation value of the stress tensor out of the integral. Then I've just got a geometric integral over this conformal killing vector dotted into the normal to the ball times the volume element, and that gives me some numerical factor. That's what I said about the ball being small. The numerical factor I get is this thing, which looks very similar to what we had before for the area variation at fixed volume. And in fact, if I multiply this by that coefficient eta, that's the universal entropy density coefficient, and add the two, remember what I should remind you, why am I adding the two, sorry. So the idea here is that the net entropy variation is the sum of these two terms, and if the entropy is maximum in the vacuum, then when I vary away from it, the variation should be zero to first order. So I'm going to set the sum of those two terms to 0. And that gives me the Einstein equation with a coefficient, 2 pi over h bar divided by the coefficient of the area, that's eta, that I called eta before. And if I just interpret this as the effective 8 pi times Newton's constant, I can read off the relationship between eta and Newton's constant. And guess what I find? It's 1/4 of 1 over the Planck length squared. So that's because these numerical factors cancel. And that was only because I held the volume fixed here. If I'd held the length fixed, something else would have come out. So I think it's a non-trivial check that the inferred entropy density that I get from the inferred Newton constant, from the inferred Einstein equation, is the same as the entropy density I would get from that Einstein equation using Bekenstein-Hawking's argument. So that seems quite satisfactory, but that was just for a conformal field. What about if we have a non-conformal field? So that formula is definitely not true, but let's just see what do we actually need to make the argument fly. So the formula I had before is this one where x equals 0. And now I want to hypothesize that if my ball is now not only smaller than the curvature and smaller than the excitation scale, but also smaller than any length scale in the quantum field theory, I'm going to conjecture that this relation holds where x is some scalar operator. And that's all I will need. I don't need to know what operator it is, just that the only tensor part contributing to the variation of entanglement entropy inside this ball comes from its stress energy tensor. Okay? I don't know if this is true, and it's just a statement about quantum field theory, and it's either true or false, and we'll know which one it is at some point. So if I try this now, and I equate the two, I equate the sum of the two contributions to the entropy variation to 0, I get this modified equation, which is a disaster because of Bianchi identity and conservation of energy. It implies that this x expectation value must be a constant, and that's not satisfactory. But at this point, I'm going to invoke the idea that the vacuum, basically the strategy here is to do whatever I have to do to derive the Einstein equation. Then we can judge at the end whether it seems reasonable or not. Okay? What I have to do is get some flexibility, and the way I'll get that is by saying, look, a vacuum need not be flat space, it should be maximally symmetric. That's what an equilibrium state is. So I'll allow for a possible local cosmological constant that I call little lambda. And then when I put in g, I should subtract off the maximally symmetric g, which is just minus lambda GAB. If I do that, then there's one more term in the equation here. And now when I apply Bianchi identity and energy conservation, I don't conclude that x variation must be constant, but rather I confer that the sum of that and lambda must be a constant. So it gives me a link between this between the cosmological constant of the local maximally symmetric space that I'm comparing to, and this x operator expectation value. And if I do that, I then get up to an integration constant, which is the cosmological constant. I get the Einstein equation. And now the bad news. So this derivation, even if you accept so far, it was only for first order changes of the matter state. And it also is not the case that all energy manifests as entanglement entropy. Like pointed out to me by Madhavan and Varadarajan, just a coherent state of a free field doesn't change the entanglement entropy in space. I can explain why later if you're interested. But that was actually noticed way back in 95 and 96 by these authors. For example, a magnetic field, just a classical magnetic field. So this is glitches in the flies in the ointment. On the other hand, I think that what we've seen so far is suggestive enough that it makes me feel like maybe there's just some missing idea here, and this can be made to really work. So now I just have to end. Let's see, these are just remarks, it's not so much a summary, but black hole entropy and several facets of ADS-CFT to date hint that in some sense, yet to be precisely formulated. Quantum entanglement may be the fabric that space-time is made of. And it's for that reason that I find it interesting to explore this connection between the maximum vacuum entanglement hypothesis and the Einstein equation. I've mentioned some open questions. Another one is, why exactly should I be holding the volume fixed? Can higher curvature corrections be understood in this framework? Since I did everything to first order in everything, it's going to be very difficult, I think, to extend it beyond that. And finally, what's the long view here? I thought I would end on this slide. So the real long view is, let's go back to thermodynamics and quantum mechanics. Clausius introduced entropy in 1854. And then something like 40 years later, Planck started working, and you may not know this, but I recently read the amazing book by Thomas Kuhn, Black Body Theory and Quantum Discontinuity, and I learned great things from it. One of which is that the reason why Planck was working on this was not to understand the black body spectrum. He wanted to show initially that the second law of thermodynamics was absolute, like energy conservation, not just approximate or statistical. He eventually realized during this long path between 1894 and 1900 that that was not a good idea, that actually electromagnetism is time reversal invariant also, and there was just time symmetry violating boundary conditions. But it got him into understanding the problem of equilibrium of radiation. And of course, as you all know, that led to quantum mechanics, much to everybody's surprise. But we didn't really have the full quantum theory until another 30 years later than when he started doing that. So here's Jacob Bekenstein at the Les Houches Summer School in 1972, when he was a graduate student still, when he introduced the idea of black hole entropy. And by the way, it was at that school that Brandon Carter took him in a back room and beat him over the head and told him that the idea of black hole entropy was silly, because of course nothing comes out of a black hole. And he was right, nothing comes out of a black hole, at least according to the Hawking effect. The pairs are peeled apart at the horizon, but the radiation that you see started outside the black hole, so nothing got out. So they were both right. Okay, so we started with him there, jump forward. Now I'm not going to try to pick one person 40 years later today, but I'm just going to list a bunch of things that emerged trying to grapple with this entropy, just like statistical mechanics, worrying about Poincare recurrences and what's Loschmidt's paradox and the arguments between Boltzmann and everybody and all that stuff. We have the Hawking radiation, the information puzzle, Unruh radiation, spatial entanglement entropy, the normalization of Newton's constant tied up with that ADS-CFT duality, Ryu-Takanagi entropy. All of this, some of it worrying about arcane things like these guys were initially. Fundamental things like, does information get lost in black hole evaporation? Okay? Is unitarity exact? And we can now extrapolate 30 years forward, and well, okay, that's the best I can do in telling you where we'll be then. But I feel we'll be somewhere, and it's going to be understanding more than we understand now. Thank you.
Okay, thank you very much for this beautiful talk. Are there comments or questions?
Just a slightly technical question. When you talk about a black hole, which space-like, what are the boundary conditions in quantum fields? What do you mean by? Surely you have to impose some kind of boundary conditions to define.
On the horizon?
Yeah. No, there is no horizon. The ball.
Oh, the ball, not a black hole?
Yeah.
Oh, no boundary conditions. The same as a horizon. So I'm imagining just this dotted, this imaginary ball in the vacuum, just sitting in it. I can talk about the reduced density matrix of the field of the vacuum state inside the ball. It's not that I've imposed a different boundary condition, I've just restricted attention to observables inside the ball. This is very much a semi-classical picture, because as we know, observables aren't locally well-defined quantum gravities. So I'm coming at it from the semi-classical side.
I understand, but in terms of, exactly in those terms, in terms of product open space.
Okay.
So I need to define the inside open space. For that, I will need some condition.
I don't think you do. I mean, will you accept the lattice regularization? Will you accept the lattice
Will you
regularization?
throw out gauge theories in this discussion?
Will you accept lattice regularization?
For gauge theory, how will that work?
Ah, okay. Gauge theory raises a hairy difficulty with the localization.
Or, let's say, gravitational saturation.
Yeah. The thing is, there's every sign, though, that those complications are correctly handled by the renormalization of the gravitational coupling. So although it's kind of, it raises questions about how we exactly identify the degrees of freedom near the surface, it doesn't seem to ruin this identification of the total, of the net quantity that's independent of scale. So I guess I'm just hopeful that that still makes sense. It seems to work for black hole entropy, so why not?
So there's nothing special about it.
That would be my take. Nothing special about our horizon. I'll go on record saying that.
Okay.
What do you really mean by the renormalization of the Newton's coupling constant? Because if you just think about GR as an effective field theory, then all quantum corrections are going just to generate higher order terms like R squared, and they are not going to renormalize G. So in this sense, I don't really understand what you mean by G renormalization.
Yeah, it's definitely not a precisely formulated thing, but I try to do it in the Wilsonian framework where you just cut off degrees of freedom at some length or momentum scale, and then have an effective action that governs degrees of freedom at longer lengths, and it's the coupling constant in front of it.
Yeah, but even in this Wilsonian renormalization, G doesn't run.
I think it has to, exactly the way it has to.
Unless your particles are massive. This is just very small running. But if you consider, for example, massless particles, then once you define G as some UV cutoff, and you run your scale down.
Actually, yeah, so I can show, there are papers by myself and Alejandro Sachs, and also by Ludi and Cooperman and Ludi, looking exactly at this flow of the gravitational couplings in relation to the flow of the entanglement entropy in a cutoff dependent way. And it seems to match, but maybe we should talk about the details later.
Another question?
Yeah, so what is very appealing, I think, from this approach is the use of entanglement as a definition of entropy. So, in fact, it is very general, and you can separate a region from outside and count the degrees of freedom. Now, my question is about symmetry. So what is the role played by the symmetry in this? I mean, you just say that black hole, the fact that you have a black hole or black hole horizon is not playing any role in this. But again, when you reproduce your argument in this little ball or diamond, you're using a conformal symmetry, which eventually will allow you to use to get back information about the thermality of the symmetrics with respect to the fact that you're looking at the Rindle wedge. So saying that we are looking at the Rindle wedge is about like saying.
Okay, but what's the point you're trying to get to?
The point is that what if we break this symmetry? Can we still get something like that?
Oh, yeah, I don't know. I think the symmetry entered my analysis by assuming that space-time was locally flat or maximally symmetric. And if I gave that up, I agree with you, I wouldn't be able to say what I said.
Okay, so there is time for another brief question.
Then I got a bit confused about the following point. One is, in the conformal field theory picture, if I consider coherent states, do I have a problem? That is my first question. The same kind of problem that Madhav and other arguments pointing out. And the second issue is...
Should I answer that first? So, no, because I'm doing a first order perturbation of the matter state. So for a coherent state, if the parameter I'm perturbing it is the coherent state parameter, I have zero variation of both energy and entropy at first order.
But do you think that this goes on to the second order? That was
yeah, well, that's what I was saying is the question.
So you posed it in the context of the non-conformally many theories, but the statement is that same question in second order is also a question for inconformity.
Yeah, definitely. I meant for those questions to be general.
Okay. And then in the theories which are not conformal theories, I got confused about your mappings and so on. So if it is not flat space, then your argument went in mapping that little patch to Rinder wedge. And now I'm something like a de Sitter space or something like that. And then the picture seems to be quite different from the Rinder wedge.
Well, you can still do it because the de Sitter space is conformally flat. So
I know, but still there is a, the difference between quantum field theory and Minkowski space and de Sitter space time because of...
conformal field theory is not going to be different because it's conformally flat.
Yes, brief question.
There was a Bekenstein argument you gave early on, which creates the impression that the area of the black hole horizon is quantized. And I think that's not the modern picture because the spacing of level. Okay, you would not. Okay.
I have an answer to that. What do you want? Yeah, I don't think it does create that impression. I mean, it may have created that impression, but I didn't mean to, and I don't think Bekenstein initially thought of it that way, although he did later explore that idea. It's just that if you ask, he was asking about changing the amount of missing information by 1 bit. So that bit is supposed to be a definite thing that he knows he's missing. Of course, you can change it by a fraction of a bit.
Okay, let's thank Ted again.